morning, everyone. Thank you all for joining. So, I will be presenting you today. Uh, my topic is designing a smart automotive front lighting system following the ASPICE process. So, I am Sohil Manikanta. I am a senior system engineer advocate at BlueKei Solutions, working in automotive domain with ASPICE, MBSE, Capella, with almost 4 years of experience. Digital engineering with BlueKei Solutions. Let me take a moment and introduce my organization. So we follow a process which is to empower decision makers in transforming business digitally by helping to manage cost and scheduling and efficiently develop systems using scientific SC methods and systematic approaches while maintaining design integrity and minimal work. So we have been served over 15 Fortune 500 companies, 25 plus industry experts, and 85% repeated customers. So this long-term trust is what drives our commitment to high quality process-driven automotive solutions. So not only automotive solutions like aerospace, satellite, manufacturing, medtech, and also railways. So we offer knowledge consulting, competency development, and project executions. So my agenda is today is introduction, challenges, approach, which is ASPICE process using Capella, value additions and benefits, and conclusion. So now, before directly jumping into the topic, let's understand the room. So to make this session more interactive, please take a moment to answer the poll questions before we begin. Yeah, let's go ahead. So product development challenges in automotive systems. So, modern automotive systems are complex and multi-domain systems like electronics, softwares, and some thermal management. So, if you see here, there are many systems like GPS navigation, electronic power roof system, climate control, radar sensor, adaptive cruise control, HID headlamp, engine control unit, airbag control, and satellite crash sensors, etc. So, there are many systems. So, like increasing in systems will increase in challenges as well. So, some of the challenges are in product development. So, like lack of end-to-end traceability, hidden assumptions between hardware, software, and sensors, lack of system-level validation before implementation, difficult reuse of legacy systems, supplier misalignment, and integration issues. So moving ahead. So why automotive lighting system? So like in the previous slide, we have seen many automotive systems. So like my use case is related to lighting system. So why? So lighting system is a compact example that spans mechanical, electrical, control, and software domains, and has strict regulatory and safety constraints. So making it ideal to demonstrate MBSE value. So, using a smart automotive lighting system case study, we demonstrate how a model-based approach supports a spice process by improving clarity, traceability, and engineering quality. So, here you can see in the image. So, like there is normal headlamp, and then the transition is the LED lamp. So, uh, for this transition, there will be common issues. So, complex sensors and ECU interactions, high integration with vehicle networks, multi-domain dependencies like software, hardware, mechanical, and then traceability gaps. So now let's go in deep about what is automotive lighting systems and how they work. So I have compared on-off switch to advanced systems. So on-off switch. So on-off switch is a combination of headlamp switch, relay, battery, headlamps, fuses, wiring harness. So with the combination of these components, the reliable headlamp operation is working. And then coming to adaptive lighting system. So we have headlamp control unit, advanced light sources, which provides efficient and bright LED laser illumination, communication interfaces, so which integrates with vehicle systems for enhanced functionality and user interface. So, which it allows drivers to customize lighting preferences easily. So, with the combination of all these things, the optimal light performance is obtained. So, here you can see the transition of simple on-off switch to adaptive lighting system. So so for example, let's take an example. So like imagine the vehicle is passing over a speed breaker at a night. As the car pitches upward, the headlamp beam briefly points away from the road. So even a 1 second loss of visibility can be risky. So a smart headlamp system detects this motion instantly and adjusts the beam angle so that the driver always sees the road clearly. So which is why the modeling is important and it matters. So what is that? ASPICE meets Arcadia. So in this presentation, I'm going to compare Arcadia layering with the ASPICE SIS1 to SIS3. So ASPICE defines the required engineering process to ensure maturity, consistency, and traceability. So here comes the handshake between Arcadia and ASPICE. So now let's understand what is ASPICE. So ASPICE stands for uh, Automotive Software Performance Improvement and Capability Determination. So it is a process assessment model, like which is PAM, and process reference model, PRM. So for software, hardware, and mechanical, so like as well as cyber security, like let's see those. So teams who design and develop products for automotive industry, so they are using the ASPICE process very much. So like let's understand this process. So this ASPICE V model shows how different engineering groups contribute their inputs step by step. So like each layer adds its own specifications, designs, and tests. So like when all these inputs come together in the correct sequence, so they form a complete high quality product. So like here you can see there are different groups like system engineering process group, software engineering process group, hardware engineering group, and machine learning group, acquisition process groups, and so on. So like when many groups contribute to a space process, the challenges also grow in some proportion. So I am focusing on sys1, sys2, sys3 artifacts. So the challenges in ASPICE. So there are some hidden risks of ASPICE non-compliance. So there are late integration issues, so which may lead for project delays, increased costs, and so on, like failed process audit and traceability gaps and poor requirement management. So let's see how uh, we can overcome this. So the ASPICE process with Arcadia. So Arcadia is a structured model-based designing framework. So here you can see all the layers. So like operational analysis layer, system analysis, and logical architecture, physical architecture. So I am focusing on operational analysis to logical architecture layer. So let's understand what are those. So operational analysis layer. So here, uh, mm, in operational analysis layer, we define about the system. So like stakeholder needs, operational capabilities, and in system analysis layer, we define so it is a black box, but we define our system as a boundary. And in and we define functions in system analysis layer. So coming to logical architecture layer, so here we allocate system functions to logical components. So here we derive logical components and the interaction between the system. So like here we know about the system and what is going on inside the system. So like let's map these to ASPICE. So in ASPICE SIS1, so like what are we capturing in ASPICE SIS1? So like we capture stakeholder needs, stakeholder requirements, as well as some entities. And in ASPICE SIS2, So like we derive system requirements and we derive some system missions capabilities as well as some system requirements. And coming to ASPICE SYS3, so like here we define system functions, logical components, and some architecture models. So now let's go in detail about each layer. So operational analysis layer. So here we don't talk about the system so like we talk about the real world operations and who interacts with the feature. So like for example, I took my use case is headlamp. So let's compare that. So in operational entity diagram, so in this we identify all real world actors who involved in the smart headlamp feature. So like driver, weather, VCU, regulated bodies, technician, VCM, etc. And then coming to operational capability diagram. So operational capability diagram, here we define what operational needs are and needs to be achieved. So for example, I'm having thermal management, water resistance, smart headlamp, basic functions, operational headlamps, so, etc. So like here we define the needs, which are nothing but like the stakeholder needs. And then we derive stakeholder requirements from the stakeholder needs. And then moving to system analysis layer. So here we define the system boundary and how the system should behave to support the operational needs. So now let's see system contextual diagram. So here we define the system boundary of smart headlamp. So and we define our system here and the interacting units, interacting actors. And coming to system requirements, so here we refine the stakeholder expectations into the system requirements. And then system data flow diagram. So in data flow diagram we show how the information flows between two functions. So like here is it is a flow of a headlamp. So like from the starting to ending, how the communication is, how the two functions are interacting, uh, that we can show it in this data flow diagram. And then goes to functional scenario diagram. So here we illustrate the dynamic behavior using a scenario. So for example, if there are any timing parameters of or there are any scenarios, we uh, define those using functional scenario diagram. And then comes system architecture diagram. So here we can define, so like there is a system and there are some external actors, so like which you can see here. So you can see the what information enters and what information leaves. So there will be the interactions between our system and then external actors. So now moving into logical architecture layers. So what are we doing here? So now we convert our system functions into logical components. So the building blocks of the solution. So in logical component breakdown, we translate system function into architecture components. So here you can see the breakdown of our system into subsystems. So like the headlamp control unit is my main system, and then TI matrix LED unit, which is turn indicator, and then matrix LED units, and then actuators, and then electric control cooling unit, and then DRL matrix LED unit. So these will be some of the subsystems for the headlamp operation. And then there will be the external actors which are derived from operational analysis layer and then system analysis layer. And then here comes the logical architecture in a high level. So you can see here this is my main system, and then there are some logical components which are interacting. So here we can define our system in a white box. And then so questioning myself. So till now we have did the modeling till logical architecture layer. So what questions can we have ourselves? So like, are there any requirements that are still unallocated, and then have I checked the model for inconsistencies or missing links? So did I validate that the logical architecture fulfills all system requirements? Is every element in the logical architecture traceable to requirement or a function? And then are all interfaces clearly defined? And then have I produced the work products expected by ASPICE? And then is the logical architecture detailed enough to start software and hardware architecture activities? So like I'm questioning myself, is this enough? Let's check. So how modeling in Capella benefit us? So using ASPICE process. So ASPICE process is a like it measures how mature and consistent your development process is. So like uh, in ASPICE cap, so like we are having ASPICE capability level from level 0 to level 5. So each level tells how well a team performs its process. So like we are having level from level 0 to level 5, so which are incomplete, which is so uh, here the work happens randomly, so not guarantee of output. And then in level 1 it is performed. So perform means, so like you deliver the expected outcomes but not consistently. And then managed, so uh, in managed the work is under control, planned, uh, tracked and documented. And comes to established, so here everyone follows the same standard process in an organizational level. And then predictable, so here you know the numbers measure performance and can predict outcomes as well. And then uh, innovating, so it is optimizing process, so which you are improving the process constantly using data. And then so let's move to ASPICE best practices. So what does this best practice mean? So uh, in each layer of ASPICE, so for example, if I take system engineering process, the system engineering group, we are having from sys1 to sys5, but I am handling sys1 to sys3. I am focused on sys1 to sys3. So like in each group, in each process, there are some best practices. So like for each process, like sys1, sys2, sys3, like sv1, sv2, like there will be some best practices which activities must be performed to achieve the process performance. So it acts like a checklist. So you must achieve these best practices to complete the process. So like I took some of the best practices which are very important to my process. So which are specify system requirements, and then structure system requirements, and then develop system architectural design. So allocate system requirements to functions and components, and then define interfaces, which is ICD table, and then ensure consistency. So these are my some of the base practices which I took. And then let's move ahead, like let's uh, deep dive into these and understand what are these base practices and how can we achieve these. So base practice one, which is specify system requirements. So what does this mean? So all system requirements, like which are functional and non-functional, are captured using templates. So before that, so like let's understand what are system requirements and what is the importance of those. So like the quality of system requirements so plays a fundamental role, especially when we consider advanced approaches such as model based systems engineering. So modern automotive vehicles are becoming complex day by day. So incorporated a wide range of onboard electronics, softwares, and mechanics to meet demands for safety, comfort, and efficiency. So like in this highly complex environment, so uh, the clear and precise definition of system requirements is crucial. So we need to follow correctness, completeness, consistency, change management, traceability, and testability. So like if you follow these steps, then uh, it will lead to this a good requirement and a success to a project. So like poorly defined or misunderstood requirements can lead to delays, additional costs, and so on. So like these are the system requirements which we have covered. And then so like how we are deriving these system requirements in Capella. So like we are having a add-on which is requirement viewpoint. So like with the help of this add-on, we are deriving the system requirements in each layer. So like we can derive system stakeholder requirements in operational analysis layer, and we can derive system functional requirements in system analysis layer. We can derive component related requirements, which are design related requirements, in logical architecture layer, and etc. So now let's move to the BP2, base practice 2. Structure system requirements. So what does this structure system requirement means? So like it is structured by domain, component, or function. So following the hierarchy is main here. So like ASPICE offers a structured approach to dealing with this complexity. So like allowing engineers to develop models that captures not only system requirements but also interacts with between system functions and components. So here comes my functional architecture, and then here comes my some of the requirements which I linked with particular functions. So similarly, I have linked component related requirements to my components. And then there is one more base practice, which is assign system requirements to architecture components. So which is you can see in this model. So like I have allocated my system requirements to my logical components. And moving ahead, base practice 3, develop system architecture design. So what does this mean? So creates an architecture that satisfies system requirements. So this is the main. And now, so here you can see we have derived system requirements, and then we have derived the we have created the architecture that satisfies the system requirements. So now, uh, so this is the architecture which you have seen in the previous slide, and then here we have applied the legends. So what does that mean? So Capella. So Capella has an add-on which is diagram styler. So with the help of this diagram styler, we can identify structure of systems. So for example, here you can see I have uh, included the properties for each system. So for example, I had to headlamp control unit, which is the gray part, as one of my main system, and then external systems, which are these, as one of my group, and then some subsystems of my headlamp, so which are different colors. So mainly this is useful for to identify which group of systems comes under which. So like for identification process, it is very useful, and then grouping purpose. So like let's move ahead. Define interfaces. So ICD table. So what does this ICD table mean? Interface, control, document. So describe the interfaces between system elements clearly and completely. So if you see in this image, so like there are source component, target component, and the exchange between them. So if you observe in the previous architecture, there are some interactions between component to component which we can extract like this in the form of Excel sheet. So how are we extracting this? Using Python for Capella. So there is an inbuilt sample scripts for some of the aspects, like from those which I took export list of functional exchanges or component exchanges. So here, why are we defining this ICD table? Let's find out. So if you observe here, the source component and target component and exchange between them. So checking for duplicates. So if you observe here, this is my source component and this is my target component, and there is an exchange. So what does this duplicates means? So Since multiple people work on the same project, they may accidentally create duplicate interfaces or define the same data differently. So using this ICD table, we can easily detect these inconsistencies and avoid duplications or interface errors. So like if you see here, so there is an exchange between BCM and headlamp control unit, which is high beam on or off. And similarly, from BCM to headlamp control unit, this is high beam on or off. So identifying these duplications and then checking for naming conventions. So there is an interaction which is from power unit to headlamp control unit, which is electrical power, and then power unit to headlamp control unit, which is also electrical power. So if you observe here, so even the caps, the power P is small here and this is caps here. So this may lead to confusion. So this so we can identify these type of errors with the help of ICD table. Not only this, and what can we do with these ICD tables? So ICD table also serves as a key input to software team, so ensuring they receive a consistent and validated set of interfaces for implementations. So let's move ahead. So relationship matrix. So in ASPICE, traceability is mandatory across all levels, like from stakeholder needs to system requirements, and then system architecture, design elements, tests, and work products. So, right, a relationship matrix helps us verify this traceability. So these are some of the inbuilt relationship matrices that we can extract from Capella. So like these relationship matrices help us meet ASPICE traceability expectations by automatically showing how requirements and architecture elements uh, are linked, and by exposing missing or inconsistency traces. So I have extracted some of the traceability matrices here. So component to function traceability. So like here, if you see, these are my components, and then these are my functions. So like which functions are allocated to which components, we can see the mapping over here. So for example, technician is mapped. So like the check for system fault. So this is a function which it is mapped to the technician. So, and then the next, which is system function to logical function. So here you can see these are my logical functions, these are my system function. You can see the allocation between them. So like in system analysis layer, we are deriving the system functions, and in logical architecture layer, so we are allocating system functions to logical components. So in logical architecture layer, maybe some of the new functions will be derived inside our systems. So those we can identify and we can map to the logical functions here. Moving ahead, ASPICE. So the best scalable path for designing smart front lighting system. What we have achieved till now, from assumptions to assurance. So ASPICE forces every requirement, interfaces, and constraints to be explicit, testable, and justified, eliminating ambiguity. So before it becomes a failure. And then architecture with intent. So what does this mean? So like what we have achieved. So from sys1 to sys3, we created a traceable chain from user need to system requirements, and to system design. So ensuring the final lighting behavior is predictable, safe, and regulation ready. And then controlled complexity. So smart lighting is non-linear and highly reactive. So like ASPICE provides a governed decision framework here, so that prevents feature interaction issues, integration surprises, and some late defect explosions. And then quality as a process outcome. So with capability driven practices, organizations don't hope for quality, they manufacture it through evidence, reviews, and repeatable workflows. And then our enterprise advantage. So ASPICE maturity becomes a competitive differentiator. So, like the faster approvals, a stronger supplier ecosystems, and then lower life cycle cost across the programs. So now I'm concluding with a tag, which is ASPICE don't make smart lighting system easier. So like it makes manageable, measurable, and reliably deliverable through discipline. So which is model based systems engineering. Thank you all.
Okay, thank you. Requirement elicitation in practice usually consists of decomposing and tracing multitude of requirement documents and standards. Are you using OA layer to remodel all existing requirements into Capella artifacts? Or are you mainly ensuring traceability from sys to level with requirement import and allocation in Capella?
Yeah, let me understand it. So this is one requirement elicitation. So in practice, usually uh, consists of decomposing and tracing multitude of requirement documents and standards. Are you using OA layer to remodel all existing requirements into Capella artifacts, or are you maybe ensuring traceability from SIS2 level with requirements, import and allocation in Capella? If the answer is SIS2 option, do you think that OA layer usage still makes sense? So here, what I understand is, so in OA layer, we are not deriving any system level requirements. So like we are deriving the stakeholder requirements. So in OA layer, we are having stakeholder needs, which stakeholders will provide. And from those, we are deriving it in a stakeholder format. So like the stakeholder requirements. So from that, we are deriving system requirements in system analysis layer.
Oh, thank you for that. How much time it took to implement advanced lighting system using Capella compared to a conventional process?
Yeah. So as compared to conventional process, as Capella is a structured a layer process, it is easy to identify which attribute goes into the which layer. So as compared to conventional process, I'm confident that Capella takes less time.
Okay, thanks for that. Well, once again, many thanks for this great presentation.